We were talking about the weighted average, and one example was we were comparing two different velocities and trying to figure out the mean velocities, right? So that's usually not what we do, at least not in this institute. So we have, usually what you have is that you have data and need somehow combine data. In our case, for example, we have observations of spectral lines from interstellar medium, as an example. Yeah? Or if we are from the lab, we have spectroscopic measurements from an experiment, where we measure emission lines of a molecule, also in the lab. Usually, these measurements, either lab or astronomically, suffer from significant noise. Yeah? And the level of noise or the quality of your data is not necessarily the same. Yeah? If I have a telescope, observe today, observe tomorrow, not necessarily the data would be of equal quality. Yeah? The properties of the atmosphere may change, my tuning of the receiver may be not optimal, whatever. Yeah? At the end, I still need to combine this. So one common choice, if we are weighting data that we have, is to take the quality of the data as a weighting factor. And the common weighting factor is the noise level in data. So what I would like to do is demonstrate this, how this is done, and what the effect is. To do this, I'm creating a function here that simulates an experiment or an observation. And what we do is we observe some spectral line, and I decide that this is a Gaussian line profile. Yeah? So it's a common profile. And a Gaussian profile is, let's do it differently, at a position, at some frequency, has three parameters. So it has a central frequency, an amplitude, and a line width. Let's call it sigma. And Gaussian is defined as x minus x0, oops. That's Gaussian function. Yeah? You know this? I guess yes. So, if I plot this, then it looks like this. Okay? So, I gave it here three parameters. So 0 is the position of the center of my line. 1 is my amplitude at the center, and 0.5 is the standard deviation, so the width of the line. Okay, so works. And then I'm suffering from noise. And let's say we have noise, random noise, that's normally distributed. I have to look up the. Okay. With some standard deviation that we call RMS. We get this random. Okay. So noise here is a function. If I provide it with a noise level, let's say 1, then it creates a random number. every time I run the function, it creates a random number that's distributed according to a standard normal distribution. We will learn later what this means in detail. Okay? Good. Now let's make some measurements. We are having a spectrograph that's taking measurements at some given sampling, so at some given x values in this case. Just to visualize this here, that's how our data looks noisy. Okay? So let's create some data. We are taking this here and at x values that vary from -5 to 5 and steps of 0.1. Let's say that's data that we measure here in Cologne in the lab. And then we have colleagues in another institute. They have a different setup, different noise level. They measure this, do the same experiment, but let's say they have a much worse experiment. Yeah? The noise level is 0.4. Now, if we plot the two data, it doesn't matter. List line plot. If I plot the two, that's how it looks like. Yeah. Let's make the lines a little bit thicker. Okay, so what we see is that apparently the blue noise is much less, so that's our data from in-house, and that's the additional data. Now, if we would combine the two directly, so taking the average, yeah, that would mean we are doing, basically, we are adding them up and multiplying by 1/2. That's not good. And this is wrong. So that looks like this, okay? And now we could start with our master thesis or whatever and quantify the result. So, but what we did is basically we combined some good and bad quality data. And by taking the average of these two here, we of course increase the noise of our in-house data. Or yeah, the mean value between the two will have a higher noise level than what we had originally, because we gave them equal weight. So first of all, the question would be, why do it in the first place? Why would we add up good and bad data? Why not just toss away the bad data?
It will help us to improve a signal to noise.
Yes. Why?
Because noise is random, and we can calculate the mean of noise, and after that we will get a lower level of noise in our signal.
That's what we saw last week with this pulsar map example. Yeah? We are adding up the uncorrelated noise, should even out in the long run. Here we only have two examples, so we are out of luck a little bit. But it's also that, of course, astronomically, to do this implicitly is by increasing the exposure times of your observations. Yeah, so if you observe long enough, you count more photons. That has some problems with stability of receiver and practical considerations, that your source might vanish behind the horizon, for example, or that at some point you need to sleep and whatever. So you split this up in chunks of observation, and at the end add them up. So what we did here, for example. Yeah? So these might be the result of 2 different observing nights. Tossing away the bad quality data would mean throwing away 50% of our time for experiment time. Yeah? So what we can do now is we can instead of just taking the mean value, we can weight our data by not taking the mean value, but taking a weighted average. And one common choice of weights is the quality of the data, or in our case, the RMS, which is the standard deviation of our noise level, or the inverse variance, for example, is also a common choice. Yeah, so that means each data gets weighted with the inverse of the standard deviation squared. This was 0.2. This was 0.4. And the whole thing is then divided by the sum of the 2. Yeah, that was our definition of the weighted average. And let's keep the initial one and compare it with the simple average. So again, the blue one here is our simple mean value of the 2, and the yellow one, it's not too visible plot here. Let's take a different time scheme. So here red is the original one and blue is the weighted average. And what we see again is here that the level of the noise level of the combined spectrum is now smaller. So that's a common application. Of course, one of the major problems is to figure out the noise level in the first place. We will do this in a second.